Okay, and then it's a pleasure to introduce the first speaker for this afternoon. That's Andres Felipe Patino, who's going to speak about complete non-selfadjointness of Schrödinger-type operators on the bounded interval. So, Andres, you have the floor.
Hi everyone, thank you so much for coming to this presentation today. It's a pleasure to me to show you our work in collaboration with Monica Winkelmaya and Christoph Fischbacher. The structure of this talk will be as follows. We start with a small definitions on dissipative and maximally dissipative operators. I will show you result in which we characterize all maximally dissipative extensions of the Schrödinger type of the Schrödinger operator on the bounded interval. And finally, we will talk about complete non-self-adjointness and specifically the self-adjoint space of all of these maximally dissipative extensions. So firstly, a densely defined linear operator A in a separable Hilbert space is called dissipative if and only if for all element in the domain we have that the imaginary part of this inner product is non-negative. And also we say that an operator is maximally dissipative if and only if the only dissipative extension of the operator is the trivial one. It means there is no non-trivial dissipative extension of A. And we also say that a tensorly defined operator B is non-negative, and we write that V is greater than or equal to 0 if and only if for all F in the domain, not the imaginary part, but the inner product between F and VF is non-negative. And observe that any non-negative operator is also a is also a dissipative operator. As a quick examples, every symmetric operator is dissipative. Every self-adjoint operator is maximally dissipative, and a quite more general for the summation between a symmetric operator in I times V, where V is non-negative, is a dissipative operator. An important result in terms of characterization of the definition of maximally dissipative operator is that a dissipative operator is maximally dissipative if and only if we have one element in the lower open complex plane that belongs to the resolvent set of A. This is equivalent to say that the whole lower open complex plane is contained in the resolvent set of A. And this is equivalent to minus A star is dissipative, and to the I time A is the generator of a strongly continuous semigroup of contractions. The main theorem the main operator that we will study in this talk is this one. Remember the minimal Laplacian in L201. This is the operator minus second derivative with null boundary conditions in F and F prime, functioned in H2 with two weak derivatives. For a non-negative bounded operator, we will say that S mean plus IB is a Schrödinger type operator in L2. Here S mean is the minimal Laplacian. V is non-negative bounded, so the summation this A mean is a dissipative operator. One thing that we studied was how calculate every maximally dissipative extension of this dissipative operator. And for that purpose, I will show you some notation. V is gonna denote a 2x2 complex matrix for a non-negative bounded operator, and for two functions in the range of V square. We define this MK matrix. This matrix depends on the K1 and K2 vectors and functions and in certain local inverse of the square root of V. This K means K1 and K2. And we assume that the imaginary part of B is greater than or equal to 1 over 4 mk, it means that the imaginary part of E minus 1 over 4 mk is a non-negative operator. With this in mind, we found a way to write every maximally dissipative extension of this Schrödinger operator. We classified it in 5 different forms, but for simplicity of the talk, and also because the other cases are quite similar to this one, we only study in this talk one of them. One of these cases is all of the extensions, all of the maximally dissipative extension of this minimal operator depends on a matrix B and a vector K, the 2 by 2 matrix in the previous slide, and the K vector. And the domain of the extensions is just relation between the boundary values of the function depending on the matrix B. And the action of the operator is minus f double prime. This term here is called a deviation, is a non-local interaction point, and this is the perturbation IBF. Here the extensions are, this group of operators are maximally dissipative operators when this condition is held. We may observe that if V is equal to 0, then K1 and K2 are equal to 0, and this matrix MK is also equal to 0. In that case, we have all of the maximally dissipative extensions of S mean, and actually, if the imaginary part of B is equal to 0, we have all of the self-adjoint extension of the minimal Gaussian. So it's like a generalization of the extension theory of asymmetry. It's similar to a generalization of the extension theory of asymmetry, self-adjoint extension theory of asymmetric operator. Okay, now the other concept that is important for a maximally dissipative operator is when it is completely non-self-adjoint. So we are going to study how this condition, depending on the matrix B, on the vectors K, this operator is completely non-self-adjoint or not. So what is a completely non-self-adjoint operator? Let me introduce a couple of concepts, a couple of definitions, and I can show you what is a completely non-self-adjoint operator. For a dissipative operator, if we take a subspace M plus subspace M, we call it reducing subspace of A if the domain of A can be split in the domain of A inter the subspace and the domain of A inter the orthogonal complement of the subspace. And the second condition says that M is invariant under the operator A. And also M orthogonal is invariant under the operator A. Something interesting in this case is that the domain of A inter M is dense in M. So the adjoint of the restriction to the subspace is well defined. And actually the adjoint coincides with the restriction of the adjoint of A in the whole Hilbert space. And once we have the adjoint, we can think in self-adjointness. So we say that a reducing subspace M is reducing self-adjoint subspace if the restriction is actually is a self-adjoint in the space M, in the subspace M. So if any restriction is non-self-adjoint, then we say that the operator is completely non-self-adjoint. It means for a dissipative operator, we call it completely non-self-adjoint, and we write CNSA for short, if there is no non-trivial reducing self-adjoint subspace of A. Any restriction is not self-adjoint to a reducing subspace. As some quick examples, if R is an eigenvalue of a symmetric operator, then the corresponding eigenspace, the kernel of S minus R, is a reducing self-adjoint subspace of S. Similarly, in this work was proof that for a real number, if this number is an eigenvalue of a maximally dissipative operator, then the corresponding eigenspace is also a reducing self-adjoint subspace. This means that if a symmetric operator or a maximally dissipative operator has at least one real eigenvalue, then the operator is not completely non-self-adjoint because the kernel is a reducing self-adjoint subspace for the operator. And the minimal Laplacian is a completely non-self-adjoint operator, and the reason is that the minimal Laplacian doesn't have real eigenvalues. Now, to understand completely non-self-adjoint for an operator, for a maximally dissipative operator, this theorem is fundamental, it's important. If for a maximally dissipative operator, there exists a unique decomposition, we can split the Hilbert space into two spaces. This is called the self-adjoint space of A. This is called the completely non-self-adjoint space of A. This is an orthogonal sum of two reducing subspaces where the restriction to the first one is self-adjoint and the restriction to the second one is completely non-self-adjoint. And it is quite clear from this result that a maximally dissipative operator is self-adjoint if and only if the self-adjoint space is the whole Hilbert space, and is completely non-self-adjoint if and only if the self-adjoint space of A is equal to 0. In the previous example, in the previous case, in this case about a maximally dissipative extensions of the minimal plus IB, the minimal Laplacian plus IB, we want to study this space. How is the shape, or what are the main characteristics of this space for these operators? Of course, if the self-adjoint space is trivial, then we say that a BK is completely non-self-adjoint. So let me define for this operator, for fixed V and K, let me define some other operators. SB hat, this SB hat, the domain of SB hat is the same domain of the maximally dissipative extension. Observe that the domain doesn't depend on K, only depend on B. And the operator, the action is minus second derivative, so this is just a Laplacian. And the SB tilde is the restriction of SB hat to its symmetric space. The symmetric space is the kernel of SB hat minus SB hat star. This restriction is important because SB tilde is symmetric. It's a symmetric restriction of SB hat, and it's a symmetric extension of the minimal Laplacian. And also SB tilde plus IB is an extension of S min plus IB, and it's a restriction of our main operator, the maximally dissipative extension. So here, this SB tilde was important because I mean, these two operators, S min plus IB and SB tilde plus IB, has a similar form. Both are a symmetric operator, which is both a restriction of SB hat, and both are dissipative. But this one is the greatest, such that it is of the form symmetric plus IB. It's the greatest restriction of ABK, which is of the form symmetric plus IB. Now, let's think for a moment in the easier case when V is equal to 0. When V is equal to 0, as I told you a moment ago, K1 and K2 are 0, so this K vector is 0, and the matrix MK is also equal to 0. In consequence, the minimal A min is just S min, of course, because V is equal to 0. is a restriction of SB tilde, is a restriction of SB hat, and in this case, SB hat coincides with the extension. Here, because MK is equal to 0, the dissipative condition is that the imaginary part of V is non-negative. And for this case, we have the following result. In this case, if the rank is of this imaginary part is at this matrix is a 2 by 2 matrix, so the rank is 0, 1, or 2. In the case of the rank is 2, we call it the non-critical case. Here, the extension is just completely non-self-adjoint. So in the second case, we call it critical case 1. Is when the rank of the imaginary part of V is equal to 0. It means that the imaginary part of V is equal to 0. And as I told you before, it means that the extension is self-adjoint. Actually, in this case, SB tilde coincides with SB hat. So, of course, if the operator is self-adjoint, it's not completely non-self-adjoint. And the more critical case 2, is when we are in an intermediate step between these two ranks, when the rank is equal to 1. Here, SB hat is completely non-self-adjoint if and only if the point spectrum of the symmetric extension of the minimal Laplacian is empty. So in certain way, this is all understood. This is we understand. We know what happened in terms of completely non-self-adjoint when the perturbation V is equal to 0. Now, what happened if for a general perturbation for any bounded non-negative operator V, but of course non-trivial, the non-critical case still remains the same. If the rank, okay, not only the imaginary part of V, but the imaginary part of V minus 1 over for MK. If this matrix is full rank, then the extension is completely non-self-adjoint, so the self-adjoint space is trivial. Now, in the critical case, unfortunately, the completely non-self-adjointness of the extension depends externally on the perturbation IV. So we fix the perturbation, or we think in specifically a potential, a multiplication operator. So let V be a non-zero multiplication operator by of course, a non-negative unbounded function. In that case, of the non-critical case remain the same because this is for general V. But in the critical case, we can say more. For if the rank is less than 2, we divide this case into cases. Critical 1 is when the rank of the imaginary part is equal to 0. Remember that it means that that imaginary part V is equal to 0. So SB hat is self-adjoint. So what we have here, self-adjoint plus IV, where V is a multiplication operator. In this case, we can prove more. We can prove that actually this extension is completely non-self-adjoint. Again, the self-adjoint space is trivial. But in the last critical case, when the rank of the imaginary part of V is greater than 0, and in this case it's just 1 or 2, probably the extension is not completely non-self-adjoint, but the self-adjoint space is not too big. It's just, of course, under a certain assumption of SB tilde, the dimension of the self-adjoint space is just, in the worst case, 2. Now, in this critical case 2, because the other ones are done, in this critical case 2, we obtain a characterization of the self-adjoint space under the assumption that SB tilde is completely non-self-adjoint. The operator ABK is not completely non-self-adjoint. It means that it has a reducing self-adjoint subspace, non-trivial reducing self-adjoint subspace, even only if we can get a function that lies in the domain of the extension, of course, that doesn't belong to the domain of SB tilde, to the symmetric restriction. and it satisfies three conditions. It's an eigenfunction. It is an equation in terms of the potential and the functions k1 and k2. And the boundary values belongs to the kernel of this imaginary part. Observe that here this kernel is non-trivial. Moreover, the self-adjoint space is generated by all functions that satisfy these three conditions. Of course, these four conditions with this one. Now, the other question was, what can we do if this condition is not true? Because sometimes the SV tilde is not completely non-self-adjoint. We can say something similar, or what can we do? What happens is if SV tilde is not completely non-self-adjoint, in that case, what we do, what was a partial answer, we add some extra condition to the potential, which is not a crazy condition, it's just we need 1 point in an interval, and a small interval in this point such that the potential is strictly positive. That's what it says. If this set AV has at least one interior point, the theorem is also true. Which theorem? The previous one. In the critical case too, under this condition on the symmetric restriction, or with this condition on the potential, we can get, of course, any proof is very different under any condition, but we can obtain that the dimension of the self-adjoint space is less than or equal to 2. And for that reason, the same result that before. A b hat is not completely non-self-adjoint if and only if there exists one function that satisfies these three conditions. And of course, the self-adjoint space is generated by at most two functions that satisfy these conditions. And finally, we also could construct that we could say that it is not an empty property. Actually, we can get extensions with that the self-adjoint space of the extension is of dimension exactly equal to 2. And it means for a non-zero multiplication operator bounded, sorry, I didn't write it, bounded, if R1 is different from R2 real numbers, then there exists a maximally dissipative operator as in the form as before, such that the self-adjoint space is the span of these two functions. These two functions are eigenfunctions of the extension with corresponding eigenvalues R2 and R1 and R2. So for any real numbers, we can get two eigenfunctions and an extension such that the self-adjoint space of the extension is of dimension 2 and generated by these two eigenfunctions. Yeah, that's all that I wanted to show you. Thank you so much for your attention. And I received your questions.
All right, thank you very much. To clap. Okay,
Thank you so
then
much.
let me stop the recording and open the floor up